Hello everyone, welcome to my YouTube channel. In this video, we are going to discuss a problem in mathematics known as Brachistochrone problem, which was given by Bernoulli in year 1696. This problem deals with the path of minimum time under the influence of gravity when a particle goes from one point to another. Actually, the word brachistochrone is made up of two Greek words, brachistos and chronos, where the word brachistos means shortest and the word chronos means time. Thus, we can say that the word brachistone stands for shortest or minimum time. This problem says that if a particle of mass m goes from point A to point B under the influence of gravity, then which path it should follow such that it should take minimum time. Alternatively, we can say that along which curve particle reaches to point B in minimum time. And in the end, we will find that this path is cycloid. Now, to solve this problem, we will use method of calculus of variation. The fundamental equation of calculus of variation is Euler-Lagrange equation, and using this equation we will solve our problem. First of all, let us discuss what is Euler-Lagrange equation. Actually, Euler-Lagrange equation gives a necessary condition for a function to extremize a given functional. This equation can be given by dy dx del f upon del y prime minus del f upon del y is equal to 0, where f is equal to f of x comma y prime. Here f is a functional, y prime is dy by dx, and y is a function of x. In mathematics, function of a function is called functional. Clearly, here f is a function of y and y is also a function of x. Thus, f is a functional. In other words, we can say that if dy dx del f upon del y prime minus del f upon del y is 0, then the integral I is equal to integral f of x y prime dx will be extremum. Using this equation, we will solve our Brachistochrone problem. Let a particle of mass m goes from point A to point B. This is point A. Let us say it is origin 0, 0, and this is point B. This is x1, y1, and the path which particle follows is y is equal to y of x. Let at any state the position of the particle is P. This is P. Coordinate of P is x, y. Distance traveled by particle in this time is s. Clearly, this height will be y. Now, from work energy theorem, we know that the change in kinetic energy will be equal to work done by particle from moving point A to point B. Since the particle starts from rest, then the initial kinetic energy will be 0. Let us say at this point velocity is v, then it will be half mv square minus 0 is equal to mgy, or we can say that v square is equal to 2gy. V will be ds upon dt. This means square of ds upon dt will be equal to 2gy. This implies ds upon dt is equal to under root 2gy, or we can say that dt is equal to 1 upon under root 2gy ds. Dt is equal to 1 upon under root 2g into 1 upon under root y ds. Let us say equation number 1. Also we know that the particle moves along this path for a very small time dt. The distance will be ds. Let us say the change in x coordinate is dx and y coordinate is dy. For very small displacement, we can write this is dx, this is dy, and this will be dx. Then using Pythagoras theorem, we can write ds square is equal to dx square plus dy square. This means ds is equal to under root dx square plus dy square. This implies ds is equal to dx under root 1 plus dy upon dx to the power 2. Also we know that also y prime can be written as dy over dx. Then we can write ds is equal to dx under root 1 plus y prime square. Using this in equation 1, we can write dt is equal to 1 upon under root 2g 1 upon under root y into dx under root 1 plus y prime square. On integrating this, we can write t is equal to 1 upon 2g integration under root 1 plus y prime square upon under root y dx. Hence, for time to be minimum, the functional f is equal to under root 1 plus y prime square upon under root y must functional f must satisfy Euler Lagrange equation. Now to use Euler Lagrange equation, first of all let us find the partial derivatives of f with respect to y and y prime. Here f is under root 1 plus y prime square divided by under root y. Now del f upon del y will be del upon del y under root 1 plus y prime square divided under root y 1 plus y prime del upon del y y to the power minus half. This will be under root 1 plus y prime square minus half into y to the power minus 3 by 2. It can also be written as minus 1 by 2 under root 1 plus y prime square divided by y to the power 3 by 2. Let us say question number 2, and del f upon del y prime will be del upon del y prime under root 1 plus y prime square divided by under root y. The term of y will be treated as constant, then it will be 1 upon under root y del upon del y prime 1 plus y prime square to the power 1 by 2. This will be 1 upon under root y 1 by 2 into 1 plus y prime square to the power minus half into 2y prime. This will cancel out. We will finally have y prime divided by under root y into under root 1 plus y prime square. Let us say case number 3. Now what we have? Del f upon del y is minus 1 upon 2 under root 1 plus y prime square divided by y to the power 3 by 2, and del f upon del y is y prime is y prime divided by under root y into under root 1 plus y prime square. Now using these values of partial derivatives in Euler-Lagrange equation, we can write using it in Euler-Lagrange equation, we have d upon dx del f upon del y prime minus del f upon del y is equal to 0. We can write d upon dx y prime divided by under root y into under root 1 plus y prime square minus half under root 1 plus y prime square divided by y to the power 3 by 2 is equal to 0. Now using the formula of differentiation of fraction, we can write denominator into differentiation of numerator minus numerator into differentiation of denominator divided by whole square of denominator, and this will be plus half under root 1 plus y prime square divided by y to the power 3 by 2 is equal to 0. Then this will be under root y under root 1 plus y prime square y double prime minus y prime. This will be first function into differentiation of second function plus second function into differentiation of first upon y 1 plus y prime square plus 1 by 2 under root 1 plus y prime square upon y to the power 3 by 2 is equal to 0. Now we will get here under root y under root 1 plus y prime square y double prime minus y prime. This will be under root y into this will be 1 by 2 1 upon under root 1 plus y prime square into 2y prime into y double prime plus under root 1 plus y prime square 1 upon 2 1 upon under root y prime upon y 1 plus y prime square plus 1 by 2 under root 1 plus y prime square upon y to the power 3 by 2 is equal to 0. Now we will get under root y under root 1 plus y prime square y double prime minus y prime into bracket under root y prime y double prime upon under root 1 plus y prime square plus y prime under root 1 plus y prime square divided by 2 under root y upon y into 1 plus y prime square plus 1 by 2 under root 1 plus y prime square divided by y to the power 3 by 2 is equal to 0. Now this will be under root y under root 1 plus y prime square y double prime minus under root y prime square y double prime upon under root 1 plus y prime square minus y prime square under root 1 plus y prime square upon 2 root y divided by y 1 plus y prime square plus 1 upon 2 under root 1 plus y prime square upon y to the power 3 by 2 is equal to 0. Now this will give under root y under root 1 plus y prime square y double prime upon y 1 plus y prime square minus root y prime square y double prime upon y 1 plus y prime square root 1 plus y prime square minus y prime square root 1 plus y prime square upon y 1 plus y prime square 2 root y plus 1 upon 2 under root 1 plus y prime square upon y to the power 3 by 2 is equal to 0. This will be y double prime upon root y root 1 plus y prime square minus y prime square y double prime upon root y 1 plus y prime square into under root 1 plus y prime square minus y prime square divided by 2y root 1 plus y prime square plus half under root 1 plus y prime square upon y to the power 3 by 2 is equal to 0. Now multiplying both sides by under root y into under root 1 plus y prime square, we get y double prime minus y prime square y double prime upon 1 plus y prime square minus y prime square upon 2y plus 1 by 2 1 plus y prime square upon y is equal to 0. Y double prime minus y prime square y double prime upon 1 plus y prime square minus y prime square upon 2y plus 1 upon 2 1 plus y prime square upon y is equal to 0. Now again multiplying both sides by 2y 1 plus y prime square, we get y prime 2y 1 plus y prime square minus y prime square y double prime into 2y minus y prime square 1 plus y prime square plus 1 plus y prime square whole square is equal to 0. We get 2y double prime 1 plus y prime square minus 2y prime square y double prime minus y prime square 1 plus y prime square plus whole square of 1 plus y prime square is equal to 0. This will be 2y double prime plus 2y prime square y double prime minus 2y prime square y double prime minus y prime square minus y prime to the power 4 plus 1 plus y prime to the power 4 plus 2y prime square is equal to 0. These two terms will be cancelled out and also these two will be cancelled out. Here we have y prime square and 2y prime square. This will be plus y prime square. Then we have y prime square plus 2y double prime plus 1 is equal to 0. Now multiplying both sides by y prime, we get y prime cube plus 2y y prime y double prime plus y prime is equal to 0. Actually, this term is a differentiation of d of dx y plus y into y prime square is equal to 0. Thus d upon dx y plus y into y prime square is equal to 0. This implies y plus y into y prime square is a constant c1. Then we can also write y into y prime square will be c1 minus y, or y prime square will be c1 minus y upon y, or also we can write y prime is equal to under root c1 minus y upon y. Now we have to solve this equation. This is a first order differential equation that has to be solved. This can be solved by using variable separable method. We can write dy upon dx is equal to under root c1 minus y upon y. This will be under root y upon c1 minus y dy is equal to dx. Let us put y is equal to c1 sin square theta. Then we will get dy is equal to C1 2 sin theta into cos theta d theta. Using this we can write under root C1 sin square theta upon C1 minus C1 cos square theta into C1 2 sin theta into cos theta d theta is equal to dx. This will be under root C1 sin square theta, and this will be C1 cos square theta into 2C1 sin theta cos theta d theta will be dx. This will cancel out, and this will be sin theta upon cos theta into 2C1 sin theta into cos theta d theta is equal to dx. And this will cancel out. We will have 2C1 sin square theta d theta is equal to dx. Also 2 sin square theta can be written as 1 minus cos 2 theta. Then we will have C1 into 1 minus cos 2 theta d theta is equal to dx. On integrating this, we can write integration 1 minus cos 2 theta d theta is equal to x plus C2, where C2 is another constant of integration. Then finally we can write C1 theta minus sin 2 theta by 2 is equal to x plus C2. This implies x is equal to minus C2 plus C1 theta minus C1 by 2 sin 2 theta. Let us say equation A. Also, we have taken y is equal to C1 sin square theta, and sin square theta can be written as 2 sin square theta is equal to 1 minus cos 2 theta, means y will be C1 into 1 by 2 1 minus cos 2 theta. Then y will be C1 by 2 1 minus cos 2 theta. Here equation A and B together represents a solution of this problem, and this is a parametric equation of cycloid. Thus, we can say that the solution of Brachistochrone problem is a cycloid. Here equation A and B together represents a parametric equation of cycloid, and we can say that the solution of Brachistochrone problem is a cycloid. In this given figure, you can see the shape of cycloid. Actually, in geometry, the cycloid is a curve traced by a point on a circle when circle rolls along a straight line without slipping.